Hi guys, in this video we're going to be learning how to read the scale on a graph. Now if you haven't done so already, please first of all go back and watch the video on how to read the scale on a number line, because a lot of the skills that we'll be using today are first of all covered in that video. However, if you already feel like you can read the scale on a number line, then let's get cracking with how to do it on a graph. So we've been given this graph here, and we're being asked to find the values of each of these columns here. So we've got column A, B, C, and D. Now we can see that the scale is going up 8 at a time. So it's going up 8, 16, 24. However, it does not tell us every station, every minor increment on this graph. And so that is what we'll need to figure out. So I know that the jump from here to here is a jump of 8. However, there are 4 smaller jumps on the way there. 1, 2, 3, 4. So, using our skills from the last video, we should know that each of these minor jumps will be 8 divided by 4. So we're dividing our major jump of 8 by the 4 minor jumps, which should mean that each of these minor increments is 2 at a time. So it's going to go up 2 on this line here, and then 4 on this line here, and then 6 on this line here, and then 8. There on it would go 10, 12, 14, 16, and we can keep going from there. So, looking at the graph then, we can see that column A is just about 1 box above 16. Now each box is worth 2, so this therefore must be 18. If we look at B, well, that's right up at the 24 mark. So that's clearly 24. Going down to C, well, that is less than 8. It's just 2 boxes, and each box is worth 2, so it's going to be 2, 4. And lastly, column D. Now this is an interesting one. It is not quite a full box. Now this line here would indicate 8. So here would be 8. Up here would be 10. However, D is only halfway in between. So D is halfway in between 8 and 10. Therefore, D has to be 9. So the scale not only applies to working out the major increments and the minor increments, but we can also use it to work out what half increments would be, what half a box would be. Now, here we have another graph in a slightly different orientation. So this one is going horizontally along the way. And again, we've got a few values to work out. Now, the major jump here is 20. It's going up in 20. But there are 1, 2, 3, 4, 5 boxes to get there. So 5 boxes between 0 and 20. So this would be 0, obviously. So in my head, I'm asking myself, well, what is 20 divided by the 5 boxes? What's 20 divided by 5? And that will give me my answer. The answer is 4. So each of these boxes must be a jump of 4. So we would have 4, 8, 12, 16, and then 20. And obviously 24, 28, 32, 36, and then 40. So we've checked it out and it seems to work out. It works out correctly with jumps of 4. So therefore we should now be able to interpret the graph. So A first of all, well, that is clearly on the 20 line that we've been given. So we know that that's 20. B, we know that each box is worth 4. So it's going to be 4, 8, 12. C, well, I don't want to start here and count 4, 8, 12, 16. That's going to take forever. I'm just going to go to the nearest one. So 20, we know where the 20 line is. That's here. And then just count on from there. 24, 28, 32. And again here, same thing. I know where the 20 line is. 20 line's here. So we're going to go 24, 28. So again, all we need to do is find what the major jump is, divide it by the number of minor jumps, and that tells us what the scale is going up in. So one final graph here. This one is a much smaller scale, a much finer scale. But again, we can still apply the same principles. So the scale appears to be going up in 20s. 20, 40, 60, 80. But if we count the number of boxes, we can work out what each box is going to be worth. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 boxes. So what I'm going to be doing is I'm going to be taking 20 and dividing it by 10. 20 divided by 10 is 2. Therefore, each box must be worth 2. Let's see if it would work. So let's see if that actually works out. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, and then 20. So yes, that does work out. Going up in 2s will get us up to the correct number. So let's work on actually interpreting this graph then. So column A, first of all, we can see that it is just past 40. So here's the 40 line. It's up at the next one. Therefore, it must be 40 plus 2. So 42. Looking at column B then. Well, it is bang on the 20 line. Therefore, it's going to be 20. Column C, well, we could do this a couple of different ways. We could start at the 40 line and count up, or we could start at the 60 line and count down. I'm going to start at the 60 line because it's nearer. So 60, this would then be 58, this then must be 56. So I'm counting back in 2s when I go down the scale. Lastly then, looking at D, well, it is almost up at the 80 line. Therefore, it's going to be easier just to count backwards. So if that's 80, this is going to be 78. So that's how we read a scale. We work out what the major jumps are and then divide it by the number of minor jumps. Before we finish, I just thought I'd throw in a bonus point about just why the scale matters. So the scale of a graph can be a really, really useful thing, or it can be a very tricky thing, a very deceptive thing. So graphs can often be used to make things look more important than they are, or to make things look less important than they are. So here we have a graph of syrup-related crimes. And we can see that between 2002 and 2011, there were no syrup-related crimes at all. So a 9-year period in which the world appeared to be syrup crime free. And then all of a sudden in 2012, we have this gargantuan spike in syrup-related crime. Obviously, syrup was suddenly in high demand, and syrup-related crime just took off at a rate of knots. Or maybe not. Instead, what we see is that the scale is very deceptive. This is a scale between 0 and 1. So yes, there was 9 years of no syrup-related crime, but this spike in syrup-related crime, this sudden increase, is actually only one single incident. So hardly something to be particularly concerned about in this case. So the scale in this graph is deceptive. Why this matters is in situations where we're given data that can have a big impact on the world. This is a graph of temperature, average global temperature around the world. And we can see all the way back in the 1880s, it was just a bit under 14 degrees Celsius. And all the way up in the 2000s, so 120 years later, it's only gone just a tiny bit higher. So it looks like the temperature has hardly changed in over 100 years. So the difference between them looks minuscule. If we actually trace out the lines between them, so there is where it started, and there's where it ended. Now that looks completely insignificant. It looks like it just doesn't matter on this graph. But the scale of this graph doesn't quite show you the full impact of this. So this scale is zoomed out too far, so it doesn't look like it matters. The thing is, if we zoom in on this graph, what we see is something quite different. We see quite a big increase overall here. So yes, the increase is just happening tiny bit by tiny bit, but it's a very definite increase. From the 1880s, we're down at just 13.7-ish degrees, a little bit below 13.7. Whereas by the 2000s, we've gone up to over 14.4, probably about 14.47 now. So there's a very clear increase. Now, looking at one graph, you would think, not a big issue, probably a load of hype. Looking at the other graph, we can see that there is definitely a trend here. There is definitely something going on. And in this case, it's something that matters at a global level and is something that we should really be concerned about. So, graphs, it's important to be able to interpret the scale in them, and it's also important to realize that the scale can be used in a way that is potentially tricky, in a way that can deceive you. Cheers, guys!